All right, so today we're going to talk more about differential equations, specifically equilibrium solutions, but I do want to do a quick preface to help ground ourselves in where we've been, where we're about to be, and then where we're going to go in the next lesson. So I just made up this quick little scenario. Let's say I happen to be an explorer and I found a new island. It was hidden, it was floating in the Pacific island, and it had a population of these animals on it. Just for the sake of today, I'm going to call them chucks. So the idea is, let's talk about how this population would grow. So there's kind of two initial type of models that most of us would go to first. This idea here, we have our exponential models. And this is what we've been studying with our differential equations thus far. And of course we mean continuous because a population is always growing. It doesn't take time off. So it's continuous exponential growth. So the idea here is maybe, let's just say 10 of those chucks made it on the island. They swam there. Since they're really good swimmers, they made it to this island in the ocean. So they would start there and then they're just going to grow, right? Because they're making more chucks. So they would grow exponentially and it would look like that. Now, maybe something else happened. This could be, maybe there was 100 million chucks and they all migrated to this new island and they got there and then they started going extinct, right? These are both continuous exponential growth models. The problem with that is it's not super realistic to most scenarios and how populations grow. What I mean by that is, let's draw another little idea here. We'll draw both of them. We had this idea of a carrying capacity making its way into our differential equations before. And the idea of a carrying capacity is more realistic to population growth because, again, let's say these same 4 chucks made it to the island. But the idea is that as these chucks start to grow and start to reproduce, they're going to start to need more and more resources, right? They need more food, they need more water, they need more space. Maybe the proportion of males to females is not right. So then there's certain individuals that can't be reproducing anymore. So this idea is they're not going to be able to actually grow forever. Eventually, they're going to reach their limit. Now, that limit depends on a lot of things, but we can understand how, again, something like resources, such as food and water and space, would limit that the growth of that population. The other thing could have happened too, though, maybe there was too many chucks there, so they didn't have enough food for everybody, but it's not like the entire population was going to go extinct. There still is resources there to support some amount of them. The last model that we could also kind of introduce right now is something called the logistic growth model. And that kind of incorporates a few things, maybe like both of these together. This is a little more advanced that we're going to do in our next lesson. But the idea is to pertain here. The idea of the logistic growth model is when the population size is small, there's a ton of resources, but there's not many population there. So I can't grow really, really fast if I start with 2 people. But as I get more and more chucks, I have more and more chucks, so I should be reproducing faster, and there's still plenty of resources. So then I hit this dream zone. Really specifically, we can see right here where the slope here, if this was our derivative, is super steep because we have the perfect mix of how many individuals there are, how many chucks are on the island. So there's a lot of them, so we can make a lot more, but there's not too much of them that we're using so many resources. And then eventually, after we leave that honeymoon period, we've just been growing so fast. Now we realize, wow, we actually have too many people, or we're going to run out of resources. So then our population growth starts to slow down and starts to level off. So today what we're going to be looking at is, rather than starting this population necessarily below the carrying capacity or above the carrying capacity, we have this general idea, or this, instance where what if it was the carrying capacity, right? What if the number of chucks that showed up to the island was exactly the number it could support? So that's our kind of grounding idea for today, is this idea of this constant value that does satisfy the carrying capacity idea. So being a little less general, we have this idea called equilibrium solutions. So here, what we have is we have 3 objects in a room that are starting at different temperatures. So we can see one of them started really hot at 100 degrees, and then it cooled eventually to room temperature. One of them started lower, so it cooled and reached room temperature faster. There was an item in that room that started below room temperature and then started to increase towards room temperature. Now, the main idea that we're noticing here, though, is regardless of where we started, above room temperature or below room temperature, given enough time, all of those temperatures ran to the to the temperature of the room. So in other words, as T progressed towards infinity, all the temperatures approached 5. So what we're kind of saying here is regardless of where we started, above or below room temperature, all of the objects made it to room temperature. So this is an idea of an equilibrium type problem. So when we look at the slope field that I pictured here, we can see two things. The function t of t is equal to 5 is a solution. The first way I'd want to view that as a solution, remember our slope field is a pictorial representation of the slopes of the solution curve. So I can see that there is a curve where every single derivative value is 0. So if I come to my equation, when is every derivative equal to 0? Well, if I plug in this function, which is just a constant of 5, I get 0. So I can algebraically guarantee that this is going to be a solution, but then we could also just visually see that this is a solution because when I draw on this curve, it follows the slope field. Now, the general idea that we're going to go through today is there's two types of examples. So we have what we call a stable equilibrium solution, meaning we have this point. Let's think again, this is like room temperature of 20 degrees. Now, if I started at 20 degrees, obviously I'm going to tend to 20 degrees in the long run. But what if I start a little bit warmer than 20 degrees? Well, in this case, if I started warmer, I still tend down to 20 degrees. Or if I started a little bit cooler, this graph shows me that I'm still tending towards that equilibrium point. So this is stable because if I make a change, it's still going back to 20. Something like this would be considered unstable. Or if I make a small change to that equilibrium starting point, like here if it's 10, if I started at 10, I'm obviously going to be 10 in the long run. But maybe if I started a little bit higher than 10, due to the function, that causes me to diverge from that horizontal line. Or maybe if I started a little bit below, it started causing me to diverge this way. That would be called unstable, because if I make a small change, then I don't tend towards that equilibrium value or that horizontal line. So those are our two main ideas. So I have two examples. This one I want to do just more conceptually with less algebra. And then I have an example here that we're just going to try to do purely with algebra. So one other thing to grab here, another common language that you'll see for these types of problems is called autonomous differential equations. Autonomous really comes from the fact that there's only one variable here, like auto by yourself, you don't need anything else, right? So like what we're saying here is what we are measuring the change of, the function that models that change is only a function of that one variable. So in this class, I'm just going to be working with y's right now, but just to kind of preface some things, we could think about the same type of differential equation using vertical lines or something. If I had the change in x with respects to time modeled by a function of x, that would also fall into that category because the variable that we're describing the change in is represented by a function of only that variable. So just language. So if I wanted to consider this differential equation, I drew a slope field here for it. So we need to use that slope field to verify that the function y equals 4, which is just a flat line, will follow the slope curve, right? So if I draw the function y equals 4, I can clearly see that it follows the rule of the slope field. So then how would I know if this is a stable or unstable equilibrium? Sorry, my thing's frozen. So what we do, this is the general outline. You visually look or you find that point where we have that horizontal line. Then we choose a point a little bit above it. So like here, if I chose a point a little bit above 4, let's just choose this one. I can see that if I was drawing these slope fields, those little lines would indicate that my slope is increasing, right? Getting farther and farther and farther away. And what I really want you to connect here, first of all, visually, I can see that those lines are tending forward. But remember what we're doing here, dy, dx, is describing how y changes, right? Is it going up or is it going down? So all these lines here, these pictures are just that. They're pictures of a positive number. Like maybe this picture is representing a slope of 5. Maybe this one here is representing a slope of 4. But what I'm noticing is that all of these slopes are positive. So if I start at a point like this, 4.5, if my y is equal to 4.5 and my derivative is always positive, well, then my y values are going to be increasing. So I should be moving away from that middle. We'll see the same thing if I choose a point that's less than 4. So I choose a point that's less than 4. I'm just arbitrarily choosing one. But if I were going to follow this idea of a slope curve, I notice that all of these lines here are negative values. They're pictures of negative slopes. So if I started at a value, let's say like y equals 3.5, and all my derivatives are going down, then I'd be moving away from that line. So I can see this picture here is if I made a change, if I wasn't exactly at 4, if I was a little bit above or a little bit below, I do not tend towards that equilibrium solution of y equals 4. So we'd summarize and we'd say that this is an unstable equilibrium. Now with that, I do want to take a quick moment to connect with the original function. And really, again, just connecting that since this is only a function of one variable, we should always be able to use separation of variables to solve these. So with this one, obviously we start to collect the variables on the correct side. And then we do all this integration stuff. And we've gone through this a lot, so I might obviously skip some steps. Kind of use that idea of these as exponents on the natural base. So y minus 4 is equal to e times x plus c to the 1 after we integrate. And then again, kind of wrapping all that stuff into one, getting rid of the positive and negative, accounting for the constant, so on and so forth that we've done. We would get y minus 4 is the same thing as some constant times e to the x. Now with this is our general solution. Now with a general solution, that's great. Let's do a little bit more and let's look at a particular solution though. So to get our particular solution, we would have had some sort of initial condition. So for instance, f of 0 was equal to that initial y value. So if we used that then and we plugged it into our general solution, we'd get this y value if we plugged in this x value. So we can see the initial y value minus 4 is equal to that constant. So if we go back to our original function, and replace c with a different representation. And then just for the sake of our function, we should just isolate y. What I want you to see here is how this original and particular solution, like this is the original function, we can see how this does describe why this is an unstable solution, right? So let's think about this for a second. Let's think about a y value that was above 4. If a y value was above 4, then the difference between y naught and 4 is a positive number. So in this situation, we're starting at 4 and we're going to add something. Well, this value is positive. And then e to the x, well, that's always positive. So if I'm starting at 4 and I'm adding a positive multiple of a positive number, we're just going to be starting at 4 and adding over and over and over and over again. So we're going to be diverging away from 4, which is what our picture showed us, right? We're diverging away. If we thought about the initial condition where our y naught was less than 4, then the difference between y naught and 4 is going to be a negative number. So in that same argument, I'd start at 4 and I would add a negative multiple of a number that's always positive. So that means I'd be starting at 4 and I would always be subtracting something. So I'm getting further and further away from 4. So just algebraically connecting this this particular solution and general solution to what we see in the slope field. And it also does do a good job at starting to get us ready for some logistic growth models. So the last example, just going through a little more algebraically. So what if I didn't have the slope field? I included it here for the sake of our picture, but there will definitely be times where you don't have a slope field, especially when we start to say that drawing slope fields is pretty difficult. As you've noticed, I've always had a computer generated one for the ones that I really need. And we don't do many by hand. So if I had to do it without the slope field, the idea here is if we want to find equilibrium solutions, the first thing we need to do, again, because equilibrium solutions, as I wrote in the notes here, are just horizontal lines. And we always know that horizontal lines have a slope of 0. So I would find when is this derivative equal to 0. And it's a pretty straightforward function here because I have it in your factored form just to ease the notes. So we can see here that y would equal 0, y would equal 4, or y could equal -2. So with that, again, pretending that I don't really have the slope field, but we can see if we did look at the slope field, that's why we get these horizontal lines at y equals 4, y equals 0, and y equals -2. Now the idea here is we need to figure out what's going to happen around those values. And this is where I want you to think about the first derivative test and critical points, right? The first derivative test was asking us, when is our derivative equal to 0? And we'd find those critical points. So in this case, let's say there was 3 of them. The idea was we wanted to know the behavior in between those critical points. So here there's 4 different regions I would need to check because there's 3 critical points. So I need a region that's below C3. I would need to describe the region that's in between C3 and C1. I would need to describe the region in between this one. And then I would also need to describe the region here, right? So we're thinking about this as a first derivative test. So when I say, okay, well, how am I going to figure out what's happening here? Well, let's choose our first time when the derivative is equal to 0. So let's just do y equals 4. Now the idea here is I want to evaluate my derivative at a point a little bit above 4 and a little bit below 4. But I have to be cognizant of these other critical points, right? So in this case, if we have a critical point at y equals 4, there is no other critical point above it. So I can choose any value above 4. Kind of like in this first derivative test, I could choose any value to test above C2 because there's no other change in behavior after that. So just for the sake of simplicity though, I'm going to use 4.5. And when I do that, and I am doing it on my calculator, I get something like 7.3. I actually don't care about the value. This is just a positive number. So the idea here is if I start at y and I'm adding a small change to y, and the change that I'm always adding is a positive number, I'd have starting at that y and I'd be adding a positive. Okay, so I can clearly tell that I'm going away from 4 then. And I would have to do the same thing below 4. Now, when I go below 4, here I have to be a little bit careful. Just like in this situation, that if I was going to try to do a first derivative test in here, I'd have to choose a point that's below C2, but it's got to be above C1. So when I'm looking at my next y value, there is another critical point at 0. So I need to choose something between 4 and 0. I am just going to choose something simple like 3.5. So when I do that, I get this value negative 4.8, but again, I don't care the actual value. I just want to know that it's less than 0. So in other words, if I started at the y value of 4 and I made a small change to x, the y value that's slightly below 4, and I made a small change to that, what I'd be really starting at is that y value that's below 4, and I'd just be adding a negative number. So my y values are just going to continually decrease. So what this tells me is if it's positive, I'm going away from that line, and since it's negative here, I'm going away from that line. So this is unstable because I'm going away from it in both cases. Moving forward to our next point, y equals 0, the same type of thing will happen. I need to choose values above and below, but again, in between where the critical points change. So above, I need to choose something between 0 and 4. I can just go ahead and reuse 3.5 if I wanted to. And I would encourage you to go ahead and choose other values too and see that maybe the value, like the actual number changes, but the sign, positive or negative, is still going to be just that same thing. Maybe I'll just choose 3 just for the sake. Oh, I can't choose 3, sorry. Oh, I can, I'm doing above, I'm getting messed up. So if I choose something above 0, like 3, I go back and I put that into my derivative. Right, we know that all those derivatives are behaving the same in between the critical points, so this derivative is less than 0. If I look at something a little bit below 0, and again, when I'm thinking about below 0, there is another critical value below it, so I can't extend past that, so let's just choose something like negative 1. When I put in negative 1, I get a positive value, which is 2.5. So the idea here that I'm thinking about is if this is 0, and I start a little bit above it, my derivative is negative, so my y values are going to be decreasing. Here, if I start a little bit below that line, my y values are always, or my derivative is always positive, so those y values are growing. So they both would be going towards that horizontal line, so this is stable. The last one we'd have to do is y equals negative 2. So the same thing is going to happen there. I can choose anything above negative 2. So like in this case, I'm going to go ahead and choose y equals negative 1, because I already know what happens there. The derivative is less than 0. If I choose something that's below negative 2, like negative 3, and again here just encouraging you to see that there is no other critical value below that, so it doesn't really matter which one I choose. It's easy just to use a nice one. So what I get with that one is I also get a, oh, I'm sorry, I made a slight mistake here. That's what I was, sorry. When the derivative is negative 1. The value is positive. So then when I plug in negative 3, I get a negative value. So what this is showing me is like if this is the line y equals negative 1, the y values that are slightly above it continue to grow and grow and grow and grow. Whereas down here, if I start at a y value below it, the derivative is negative, so they continue to decrease. So this is going to be a unstable solution. That's all I have for today. You can kind of use this as a summary page for yourself.